Hi, everyone, and welcome to Lesson 3 in Module 7, where we're going to look at the first part of the gas laws. So, what happens to the pressure when you decrease the volume at a constant temperature? Remember, we said in the last notes, we want to think about pressure as collisions. So if you take some gas in a container and you make that container smaller, are you going to have more or less collisions? You're going to have more collisions and therefore more pressure. So if I decrease the volume, I'm going to increase the pressure. Okay, let's look at the next one. What happens to the pressure when you increase the number of moles of a gas at a constant volume? So I've got a container that has gas in it. I add to the container without changing the size. I'm going to increase the pressure because now there are more things in there to increase the number of collisions. So if I increase the number of moles, I'm going to increase the pressure. How about what happens to the pressure when you increase the temperature? Got a container, it's got a gas in it. The container size does not change, which that is known as a rigid container. And you increase the temperature, you heat up those molecules inside are going to move faster. If they move faster, they're going to have more collisions with the side of the container and therefore increase the temperature. What am I doing? Increase the pressure. Increase temperature, increase pressure. Okay, and again, we want to just think about this as collisions. Pressure is collisions. So Avogadro's law says the volume of a sample of gas is directly proportional to the number of moles in the sample at constant temperature and pressure. A good example of this would be a balloon. If I put moles of air into the balloon, the volume will increase. If I let go of that balloon, the volume will decrease as the moles escape. Okay, that's a simple one. No real calculations with Avogadro's law. Next one, Dalton's law of partial pressure. Dalton's law of partial pressure states that in a mixture of gases, the total pressure is the sum of the partial pressures of each gas. Okay, so basically, if I've got a mixture of gases, all I have to do is take their individual pressures, add them up, and that will be the total pressure. Very simple. So if you look here, I've got nitrogen, oxygen, carbon dioxide, argon, and other gases with their percent by volume, and then their pressures in kilopascals. So you literally, as long as they're all in the same units, you just add them up. Okay, and so they're all kPa, kilopascals. I just add them up and I get 101.32 kilopascals, which is the atmosphere. Okay, so this is the composition of the atmosphere. All right, simple, very simple. Next gas law we're going to look at is Boyles Law. Boyles Law is the relationship between pressure and volume. So here we have a graph. It says as pressure increases, the volume decreases. So if I increase pressure, I'm going to decrease volume. Or if I decrease pressure, I'm going to increase the volume. So they're opposites of each other, which answers question C from this graph. Based on the shape, describe the general pressure-volume relationship. That is what we know as an inverse relationship. As one increases, the other decreases. So we can answer A and B here. When the volume is 2 liters, okay, so go up to 2 liters. What is the pressure? Easy, 50 kPa. B, what would the pressure be if the volume were increased to 3 liters? So we're just going to extend our graph out, which is known as extrapolation, to see where it would be if this was about 3. And you just go over, and again, it's estimation. I'm going to say about 40 kilopascals. Okay, so you're just estimating based off the trend of the graph already. So Boyle's law, again, is an inverse relationship between pressure and volume. Knowing these relationships is going to be very important later on when we start working with them more. So the equation for Boyle's law, P1 V1 is equal to P2 times V2. Very simple. I mean, really, it's I mean, I can't really make gas laws any simpler than if you know the equation, then you're going to be fine. All you need to do is, as you're reading through the problem, is point out what piece of information is what variable. So if you said, if this first example says I have 27.3 liters of oxygen at 74.2 kilopascals, then I'm going to increase that pressure to 96 kilopascals. What is the volume? So 27.3 liters, that is going to be my initial volume. 74.2 is going to be my initial pressure. Then I increase the pressure to 96, so that's my P2. What's the volume? That's my question mark. Okay, so now you just plug it all into your equation. So I'm going to take 27.3 liters, 74.2 kilopascals, they're multiplying each other, is equal to X times 96 kPa. When you do that math, X will be 21 liters, keeping your 2 sig figs based on 96, which has 2. Okay. The only thing you need to do when doing this is make sure your units match up. So if you're doing, if you have 2 pressures, those pressures just need to be the same unit in order for you to do this math. So when I divide it by 96 kPa, the kilopascals cancel out and you're left with liters, which is what you want. What is the pressure of gas if the initial volume is 12 milliliters, so that's V1, at 800 torr? Torr, another unit of pressure, okay? So we don't really need to worry about any kind of conversion for that. But I want to know what is going to be the pressure when I increase it to 50 milliliters, and that's V2. So here I've got 2 volumes. As long as the units are the same, I can do this math, which they are both milliliters, so it's fine. No need to convert it into liters or do anything with it. It doesn't matter. As long as they're the same, they'll be able to cancel out. Divide both sides by 50 milliliters. Milliliters cancel, you're left with the unit of torr. Now, my sig figs are going to be 1 because 800 only has 1, and my answer is going to be 200 torr. Keeping those sig figs with me. Okay, that's the first main gas law. Well, I guess second because Dalton's law is important. Next, we have Charles' law, the relationship between temperature and volume. So it says as the temperature of an enclosed gas increases, the volume increases if the pressure is constant. So if I increase the temperature, I'm going to increase the volume, and the opposite true. Decrease the temperature, decrease the volume. What kind of relationship is this? This is a direct relationship, okay? Which is B. What happens to the volume as the temperature rises? It increases because it is a direct relationship. Part A is asking, what's the unit of temperature? Unit of temperature is K. So when we do this, when we do gas laws, we do Kelvin only. Okay, it's important that we do Kelvin only because if we were doing degrees Celsius, there's a possibility of having a negative, which would end up leading to like negative volumes, which don't exist because we're not creating black holes. So it's important that we note that we're always using Kelvin when talking about gas laws. And finally, if the temperature of the gas were at 0 Kelvin, what would the volume of the gas be? Okay, you might want to say, okay, if I continue this graph down at 0 Kelvin, it's going to give me a volume of 0. But hopefully to you, that answer doesn't make any sense because does the thing disappear? Is its volume just gone? No, it's going to be super, super small volume, but it's still going to be there. So it can't be 0. Okay, the equation, V1 over T1 is equal to V2 over T2. And of course, we need Kelvin only. In order to get to Kelvin, we just add 273 to the degrees Celsius. So same thing as we did with our Boyles law. As we go through, we can label it. And what I also like to do as I go through, I just like to immediately change it to Kelvin so I don't forget. So if A sample of gas occupies 6.80 liters at 325 degrees Celsius. Convert that, it's 598 Kelvin. What will its volume be at 25 degrees Celsius? No, 298 Kelvin, if the pressure does not change. So this is V1, this is T1, this is T2. What is that? And so I'm looking for the new volume. Just plug it in. 6.80 liters over 598 Kelvin is equal to X over 298 Kelvin. In order to solve for this problem, you cross multiply. So it would be 6.80 liters times 298 Kelvin is equal to X times 598 Kelvin. Divide both sides by 598 and you'll get your final answer, which is 3.39 liters. Every number that I used in my calculation had 3 sig figs, so my final answer needs 3 sig figs. Pretty simple, okay? Like I said, gas laws should not be difficult. If you know your equation, you're just plugging the information in and doing your calculation. Example 2, exactly 5 liters, so that's my V1, of air at negative 50 degrees Celsius. Negative 50 degrees Celsius gives me 223 Kelvin. Is warmed to 100 degrees Celsius, which is 373 Kelvin. What's the new volume? That's T1, that's T2. So again, same thing, 5.00 liters over 223 Kelvin is going to be equal to X over 373 Kelvin. And you do that math, 8.36 liters. Pretty simple. Again, as long as you know what the equation is, are able to plug in that information, not a big deal. Of course, Kelvin only. Gay-Lussac's law has to do with pressure and temperature. It says as the temperature of an enclosed gas increases, the pressure increases. Simple. What would that graph look like? Well, we would have temperature in Kelvin on the bottom. We have pressure in whichever unit we want on the y-axis. And then if it's a increase in temperature, increase in pressure, it's just going to be a straight line because, again, this is a direct relationship. Simple. So the equation is going to look very similar to Charles' law, but we're doing pressure instead of volume. So Gay-Lussac's law, P1 over T1 is equal to P2 over T2. Again, we're just cross multiplying and then dividing in order to find our answers. So example 1, a sample of nitrogen gas has a pressure of 6.58 kilopascals at 539 Kelvin. If the volume does not change, what will be the pressure at 211 Kelvin? Okay, simple. Plug it in. 6.58 kilopascals over 539 Kelvin is equal to X over 211 Kelvin. Again, cross multiply and divide. 2.58 kilopascals will be your final answer, which makes sense. I'm decreasing my temperature. I'm going to be decreasing my pressure. And then finally, example 2 says the pressure in a car tire is 198 kilopascals at 27 degrees Celsius. I'm going to change that to 300. I'm going to put a decimal there just so that I can have 3 sig figs. After a long drive, the pressure is 225 kilopascals. What's the temperature of the air in the tire? Assume that the volume is constant. Okay, again, I've got all of my information. P1, T1, P2. My T2 is my question mark. So just plug it in. 198 kPa over 300 decimal Kelvin is equal to 225 kilopascals over X. Do that math. X is 341 Kelvin. Okay, so real life important example, not to overinflate your tires, because as you drive, and depending on how hot it is outside, as you drive, the pressure is going to increase because the gas molecules will be heating up, and therefore you have the opportunity to pop your tire, which is not good. Okay, and finally for today, we're going to stop with this last gas law, the combined gas law. So the combined gas law allows you to do calculations for situations in which only the amount of gas is constant. So the pressure, the volume, and the temperature are all changing. You can see here, P1 times V1 over T1 is equal to P2 times V2 over T2. It literally combines all the other gas laws, Charles, Boyles, and Gay-Lussac into one. So like if I know that the temperature is constant, if you hold, I'm covering temperature like you can see it, but if you cover the temperature, it's P1 times V1 is equal to P2 times V2. So that's Boyle's law. Okay, so you can see you can get all of the gas laws from this depending on what's happening. So these questions, again, very simple. All you have to do is plug in the information as you go along. So a gas at 155 kPa. So that's going to be P1. 25 degrees Celsius, I don't think so. 298 Kelvin, so that's T1, has an initial volume of 1 liter, V1. The pressure of the gas, okay, P2, 605. As the temperature, nope, not 125 Celsius. That's going to be 398 Kelvin, T2. What is the new volume? V2. Okay, very simple. I've got all of my information. I'm literally just going to plug it in. 155 kPa, 1.00 liters over 298 Kelvin will be equal to, I don't have the space, so I'm going to have to do it over here, 605 kPa x over 398 Kelvin. So again, same thing, you cross multiply and divide. So what that would look like, I'm going to do it down here, but then I'm going to have to erase it to do the next one. 155 kPa times 1.00 liter times 398 Kelvin will be equal to 605 kPa times x times 298 Kelvin. You rearrange and solve, well, you divide both sides by 605 times 298. Get x by itself. We all know how to do algebra, so I'm not going to bore you with the details. 0.342 liters. I end with sig figs because I end with 3 sig figs because all of my measurements have 3 sig figs in them. Okay, I'm going to have to erase this, so if you need to pause, please do. And then we can do the last one. Okay, so a 5-liter sample of air, so that's my V1, has a pressure of 107 kPa at a temperature, nope, not -50. We're going to turn that into Kelvin, 223 Kelvin, which is my T1. The temperature is raised to 102 degrees Celsius, which is 375 Kelvin. So that's T2, and the volume expands to 7 liters. What is the new pressure? Okay, again, I've gone through the problem. I've labeled them as I go. So I'm just going to plug them in and then do my calculation. Let's see, x, 10.00 liters, 375 Kelvin. Rearrange and solve for x by itself. The answer is 129 kPa. Pretty simple. Again, we shouldn't be stressing on these gas laws. They're pretty straightforward. What's the equation? Plug in the information, and you're good to go. That's going to be it for this lesson. Make sure you ask your questions in the chat or at the end of class so that I can answer them, and I will see you soon.